Hey everyone, today we're looking at Unit 5, Lesson 4 on the Pythagorean Theorem. And this lesson is going to be from Module 7, and it's Lesson 17 and 18. And we're going to look at the Pythagorean Theorem in terms of its distance on the coordinate plane, with our first objective being students determine the distance between 2 points on the plane using the Pythagorean theorem. So I'm going to take a minute and draw a little coordinate axis, and I suggest you do the same. I'm going to make it go maybe about 8 squares wide and 7 squares tall. And I'm going to label negative 1, 2, 3, and 4, positive 1, 2, 3, 4, and then my y-axis 1 through 5. And I'm going to look at a few points. The first is negative 3, positive 2. The second is positive 3, positive 2. And I label those A and B. And I want to know what is the distance between A and B. So I look at my coordinate grid and I count my spaces, and I know I have 6 units between those 2 points, A and B. I'm going to draw 2 more points, C and D, and decide the distance between C and D is 2 spaces. But what if I wanted to know the distance between 2 points that were not on the same vertical or horizontal line? For example, what's the distance of AC? So I'm drawing kind of a dotted line between A and C. And what you can kind of see here is that there's a triangle, and it is a right triangle because it's on the coordinate grid. And we can use that information to figure out the length of the hypotenuse. So the first leg of the triangle is from A to actually D, and that's got a length of 5. The second leg is from C to D, and that has a length of 2. And when I plug it into my Pythagorean theorem, I get 5 squared plus 2 squared equals c squared. 25 plus 4 equals 29. And the square root of 29 is approximately 5.34. So that would be the distance between A and C. So given any 2 points on a coordinate grid, I can use the Pythagorean theorem to determine how far apart they are. And in order to do that, I'm just going to write out these quick instructions. So to determine the distance between 2 points on a plane, begin by connecting the 2 points with a straight line. Draw a vertical line through one of the points and a horizontal line through the second point. And where that vertical and horizontal line intersect is going to be a right angle. So what that means is I can use the Pythagorean theorem to solve for the distance between those 2 initial points, just like we did in the example above. When we look at Module 7, Lesson 18, it's really more about real-world applications of the Pythagorean theorem. And a big assessment that you are going to have this week is a project on the Pythagorean theorem that you are going to write yourself, and it's going to be based on real-world applications. So this is just an example of one idea you might have. Our objective is going to be students apply the Pythagorean theorem to real-world and mathematical problems. And we're going to make those in 2 dimensions. We don't really want a 3-dimensional problem because it's going to be a little more complicated. So my first example that I'm going to show you, the only example I'm going to show you, is a soccer goal. So when I look at a soccer goal, there are definitely some right angles there's a rectangle. There's some interesting things. So instead of using my ruler, I'm just going to sketch 2 vertical lines that are the same height with their own kind of diagonal tail. I'm going to connect the 2 tails and then finish my soccer goal just as shown. I'm going to label some side lengths, 3, 8, C, 10. So take a moment, make sure your image looks like mine. And what I want to do is find the length of C. Well, clearly I have a right triangle with legs of 8 and 3. So 8 squared is 64 plus 3 squared is 9 equals 73. Square root of 73 is approximately 8 point, let's look at our calculator. 8.54. And then what I want to know is how much net would I need to cover that goal? Or what's the surface area? How much area does the entire goal take up? So what I'm doing is kind of highlighting the fact that there are 2 triangles and 1 rectangle that make up the area of that net. The rectangle has an area of 10 by 8.54, which is that side C we solved for, which gives me about 85.4 square feet. The triangles, even though there's 2 of them, they have an area of 2 times, and then my triangle area formula, 1/2 base times height, is 1/2 times 3 times 8. I add up the areas of the parts that I found, and I get a total area for that net of 109.4 feet squared.